If you can define a block of work, you can stream any source in Spark. Today, I'm joined with Yogita, who processed the Ethereum blockchain with Spark streaming. The same pattern works for REST APIs and more. Yogita, can you introduce yourself and share what you built?
Hello, everyone. My name is Yogita, and I've been working as a data engineer for the past 4 years, building end to end data pipelines using Azure and AWS. So, basically, when we talk about ingesting data from Ethereum, it's not like pulling data from a database or a CSV file. The data lives on a decentralized blockchain. To access, you typically have to call an API exposed by the Ethereum nodes, like the JSON RPC or Web3 APIs. These APIs return data in a deeply nested JSON format, such as blocks, transactions, smart contract logs, and so on. While Spark ships native streaming sources for Kafka, Kinesis, and S3 ADLS, Ethereum Node API aren't one of them. In this demo, I will walk you through how we have built a custom reader and how the custom reader ingests the Ethereum data in a streaming fashion.
So, by the way, this pattern is very repeatable. A lot of times I see people ingesting data from REST API calls and throttle themselves. They'll get a lot of rate limiting errors. So, what we are showing is super repeatable, where you can take this code, edit it a bit, and make any REST API source ingestion happen.
Absolutely. Thank you for your comment here, Chitesh. So as you can see that we have built this custom reader API. So before we call in the custom reader function, like we have to do few setup of the catalog where you need to pull the data into. Everything is handled by the code itself and it is done automatically. So the first block of code is essentially handling the creation of the catalog and the remaining folders, such as checkpoints folders. So let's get right into execution.
And just to clarify, this your target here is a delta table,
Yeah, exactly. Uh,
right? And technically, you can replace this delta table with Kafka or Kinesis or anything else you like.
yeah, exactly. Let's execute the second cell. The checkpoint is a really important folder for the Spark structured streaming. So essentially saves all the metadata about the checkpoint and offsets in this particular folder.
That's another common mistake which people do. People actually keep the checkpoint in the DBFS, which is not the right place because it's a throwaway space. You should always keep it in a Unity catalog volume. Unity catalog behind the scenes is a S3 and a AD list location. So it will remain no matter what happens to the workspace.
Absolutely. This is the main custom reader function, which has been implemented to read the Ethereum data from the API. As I had mentioned, what you need for the Spark structured streaming, essentially these five main functions which you need to implement and tell Spark how to retrieve the data from the Ethereum blockchain. And that is what is done in this block of code. We have functions for initial offset, which is the starting offset for new streaming queries. When it starts fresh from scratch, this is the function which gets called. Latest offset returns the latest available block from the blockchain. This is called frequently in every micro batch trigger, and it is called before partitions for each batch, and it is called on the driver node. Moving on, we have the partition functions, which essentially creates the partitions for the parallel block processing. So this is called after the latest offset and called on the driver node. And it determines the parallelism for this batch. You have the very important function, which is the read, which reads the actual blockchain data for a given partition. After partition returns a partition objects. This is called in parallel on the executor nodes. Each executor processes one or more partitions.
A couple of questions, look, then just want to understand if I am following correctly. So can you go back to the image which you had? As long as I am able to implement the initial offset and latest offset partitions and read functions, then technically I can ingest any API based source. It does not matter which API. Let's say Shopify, Stripe, let's say GitHub, just for an example. Is that a fair understanding?
Yeah, I think so. These are the main functions which Spark structured streaming expects. If you implement these, you can read from any of the APIs.
Okay, so in your Ethereum example, how did you figure out the initial offset and the latest offset?
So basically, when you call this custom reader, the first offset which you can pass as a constant value. When I am executing for the first time, I am taking the actual block number and subtracting it by 200. So that becomes the initial offset. So in this block of code, I pass the first offset, which is the initial offset.
But technically, it could be the first block on Ethereum blockchain also, right? This is just for demo purposes, you have limited it, if I'm
Ye-
inferring it.
Yes, that's correct. It could be the first block on Ethereum blockchain, but that could be a huge difference between the initial offset and the latest offset. So
So thinking about it differently, say till today, I have been ingesting data using a third party tool, and I have ingested till block number 1 million. And tomorrow I want to start processing from block number 1 million to, and after that, I want to deprecate my third party tool. Then is that the right position for Spark streaming? Because everyone is going to have some data which already exists, right? No one is going to start from scratch. Is that a fair way to replace this third party connector?
yeah, if you have already ingested 1 million blocks and then you want to start with the next number, you will pass from that number over here, and that would be your initial offset.
And what about how did you identify the latest offset in your scenario?
Latest offset is essentially calling the same API and getting the latest block number from that API. That becomes your latest offset. So for the first execution, you'll have the initial offset, which is minus 200 and up to the latest offset. So the first time, only 200 blocks will be executed. Thereafter, whenever time has elapsed, those many blocks will be executed.
Okay, sounds good.
Yep. So that's all the functions we have implemented. And this is the last block of code where I am calling the custom reader function using this line here, which says format Ethereum. In real world, if you want to read some different kind of data such as CSV, JSON files, you pass that keyword over here, say JSON or a CSV. Similarly, we have passed Ethereum as a keyword here. What it does under the hood, it calls the Ethereum function and does all the processing of reading the Ethereum data, distributing it into partitions, and then reading it into a data frame. So for that purpose, we are essentially passing all this options here, which is the schema, then the Ethereum URI, which is the API link with the API token, your unique token. Shuffle partitions is we have passed 20 and max retries is 3. So this block of code will read the data. And after it is read, we have saved that data into a delta form and to an output table. The trigger is available now is equal to true. So essentially, it will read all the data and then stop.
How did you come up with 20 as shuffle partitions and why?
Shuffle partitions we have set to 20 because we want to conform to the rate limit for the API. which allows only 20 requests per second. Hence, we have put that number 20 here. For this trigger available now, we want to process the data in an incremental fashion, not in a continuous streaming fashion, because we don't have that kind of use case here. So we decided to use available now is equal to true for this particular use case.
But that's swappable out, right? The code does not care whether you use available now or processing time for real time processing, right?
Yeah, absolutely. You can add processing time equal to set a time also.
And if
Okay.
someone has a different source which allows higher rate limits, they can go as fast as the REST API allows. So we want to go at that max speed, but not exceed it. Okay, let's get into a demo then.
Yeah, absolutely. So I will execute this last block of code and let's see how that works. So yeah, there's some comments here which are coming from the code itself. And as you can see, we have made sure that there is a difference of 200. As you can see, 4 tasks are running in parallel.
This
Sure.
4 is coming because of your cluster. You only have 4 cores available.
Exactly. Yeah. Uh,
Okay, cool. Sounds good.
We are executing 200 blocks. We are in one, and there'll be 20 tasks plus one. If you click on view, you can see how the task has been distributed among the different executors. So the cluster essentially has 4 cores, and at single time, 4 tasks are executed in parallel. So as you can see, there are input records and output records over here. And if you click on next here, you can see the 21 task. Yeah. So here it is 20 tasks, but there's one to accumulate all the results. The data is written to the output table. If we display this output table, you can see the records here. But if you see the min and max here, which says 742 minus 542, which is 200, that 200.
Okay. So it's inclusive. So that's why it's maybe 201. Sounds good. So what if you run the job again? What happens?
Yep. So we can try running it again. Can I quickly show the checkpoint?
Oh, yeah.
Let's see the checkpoint, which folder was created here.
Okay. So here is our checkpoint. Checkpoint has these 3 folders.
So here you have the offset, right? So the 200 blocks which were executed, and it will store the number which needs to be executed for the next run.
Can you show us the checkpoint? What does the checkpoint look like?
Yep. So you have this number here, which is 743.
And how does 743 match what you passed in your code? When the code was running, can you show us the output? Something was written on the UI, right?
So the last number, the blocks were processed till 742, right?
Yeah.
So essentially, checkpoint will save the number for the next execution. This is plus one. Then
Got
max
it.
offset plus one.
Okay, cool. So your checkpoint location is fixed because
Mhm.
checkpoint needs to remember where did we start and from where to start.
Exactly.
We have run the job a couple of times. I see a new checkpoint was created. Can you show us what's in this checkpoint number?
Two. Yep. So checkpoint two is 7.713806. So the second execution was this, and maybe let's see what is checkpoint one. Checkpoint one was this 7.3. So the difference for the second execution, the difference was 25 to 30 blocks or something. And for now, we are running it in a continuous streaming fashion. So you can see that it is keep running it.
Can you
Uh,
show us the Spark streaming UI on this one? Can you show us the graph? Yes. Okay, cool. So we have an input rate, we have a processing rate, we are committing every 3 seconds roughly. The input rate and processing rate is small because Ethereum blockchain does not produce enough data, right? How do you interpret the input rate and the
processing rate. Okay, so put rate is basically how many records getting processed from the API, and processing is a Spark processing rate. You can see that the rate is higher. The Spark is processing at a higher rate.
Yeah. Okay, cool. Can you show us the checkpoints folder from the Unity catalog interface?
Yep. So let's go to checkpoint.
Okay.
So we have ton of checkpoint files created here.
Yogita, what's the most important thing which people should look out in the offset folder?
I would say check at two folders, like basically offset and commits together. If the data has been processed successfully, then that particular file has to be created in the commits folder as well. And so that for the next execution, you it needs to be from the next file number.
Okay. And what if you kill your stream right now? What happens then? So how does Spark recover then?
So if I stop the execution, then the last offset which was saved, basically Spark will ensure that it doesn't execute the same offset again, causing duplicate data. If, for instance, you have an offset folder created, let's say 15, but the same was not committed, you will have the offset folder, a file year 15, and in the commit, you won't have that file. So in the next execution, it will restart from, it will reprocess the offset file 15, number 15, so that it processes and saves the data correctly.
Let's talk about a scenario, right? AWS had an outage
Yeah.
and say you can't start a cluster for a couple of hours. Then your stream is going to start after a large gap. How would you recover from that scenario?
So let's say you have a large gap and you need to restart your query. Essentially, in this custom reader, one important point is that you cannot set a batch size. Like they could be like one day you could have 100 blocks, second day you could have 200 blocks. But if there is a gap between the execution, the gap could be much higher. So in this case, let's say you have a large gap, and the last, like in this example, you have a checkpoint offset, which is this number, which is 65850. You want to start processing from this number to the latest offset. The difference is 6,000 blocks. Sparse structured streaming can easily reprocess the data from the checkpoint offset to the latest offset. It will process the data, distribute the processing to the partitions. As you can see, 6,000 blocks were executed successfully across the 20 shuffle partitions. And here is the screenshot for that. At the end, when the execution completes, the data is saved into the output table, and the checkpoint offset number, which is the last offset plus one, is saved to the checkpoint file.
Why is the plus one important?
Because when you are restarting the execution, it knows that it has to execute from that number
It avoids duplicate processing, right? It helps establish clear cut boundaries.
boundaries.
So Yogita, looks like a good demo. Looks like a lot of time must have gone in building this. So if someone is supposed to build their own, how would you explain this end to end? How does this thing work?
Absolutely. In short, the custom reader, as I've mentioned, we basically need to implement the five basic functions, which is, as you can see, like over here, the initial offset. So the offset value, where you need to exactly start. So you need to tell Spark, implement the initial offset. So in this case, you have the initial offset set as 1,000. The latest offset is what is the latest value, which is in this case 1,100. You need to set that value. And you need to execute the blocks from latest offset with some initial offset to latest offset and split it to the partition. So you always, it is the distributing those tasks among the partitions, and which will be taken care by the partition functions, and that will be distributed among the executors. So in our case it was four executors because you had four cores create which was set, And as you can see, for those flow, four executors execute or process the four blocks of code in a parallel fashion, which follows the Spark parallelism concept here. And at the end, it will all come together and get all the consolidated data back to the data frame and writes back to the target table. And in the end, you commit the checkpoint. This is the first scenario, batch one. And for the rest of the scenarios, batch two and onwards, which is essentially when you have an existing checkpoint, Sparks reads the checkpoint, which is the last offset or the checkpoint offset, which is 1100 in this case. And you get the latest offset from the latest offset function, which is 1150. Spark processes the data from the last offset to the latest offset. So rest the remaining functions are called as usual, which is partition, reading, committing, and saving to a checkpoint. And the cycle continues. So this process is same for the rest of the execution.
The takeaway here
Mm.
is, in terms of execution, the initial offset function is only called once if the checkpoint location does not exist. Okay, cool. Let me summarize this up. One sec. I'm going to share my screen. Nothing goes to production without edge cases. Let's
Yep.
cover the edge cases we came across while reading this. First scenario is, hey, what if the Ethereum nodes goes down, or if your source goes down, which eventually all sources go down. Your function can have some retriable code in it, such that if API call fails, then you don't want to fail the whole partition. So that's one thing we did in our code, which is we controlled how many times we retried. So in our scenario, we tried a retried thrice. After that, the Spark task will fail if it does not succeed. To deal with large batches, essentially, we can go as fast as the source allows. And then we want to also be reasonable about how big a Spark task can be. You can do that math and control how many shuffle partitions you end up with. How fast can you go, or processing rate one should shoot for? So ideally, I like 10x faster. Sometimes it's not possible. So when you're looking at your input rate and the processing rate, aim for 10x. If you can't do, at least do a 3x. Why is 3x important? Because you have an outage for 3 days to recover in a day. That's where the processing rate has an impact. In our scenario, we were rate bounded by how fast our input source was. So that's why we did not see a 10x, we saw like a 5x. So again, Spark is very good at throughput. So you'll most likely be input rate bounded. Another thing which is really important is determinism. If you give the same input, you should get the same output. In our scenario, we were making a get call. So your input, if you give it, in our scenario, we give a block number. No matter who calls this function, it will always get the same output. If your source itself break this contract, then you will get duplicates. So that's very important note for your source, which is your source should be deterministic. If you give a deterministic input, you should get a deterministic output. Let's quickly wrap up on what you need to do when you're making your functions. The functions which you need to implement is initial offset. This one, for you to note, is it runs on the driver. It's only called once per checkpoint. The latest offset function is executed every micro batch. So every micro batch you will run this. You get that? So latest function is executed anytime the micro batch is run. It's executed the start of the micro batch. In our case, we go to the blockchain and figure out the latest outstanding block number. We get that output. The partitions function is how you spread your work, and the read is what actually does the work. So that's the difference between partitions and read function. Then there is a cleanup function, which is called commit function, meaning if you're doing some, you were producing some external files, or you were doing something, you are producing some variables and you wanted to clean them up before you exited, that's where commit function comes in. Ideally, you shouldn't have any variables. You can do external API calls here if you want to, but essentially you'll be increasing your latency. So try to do the least amount of work. But yeah, that's about it. There is a limitation right now with the Python API, which is the first micro batch tries to process everything from the start offset to the end offset. As we speak, we already have some things on the roadmap. I'll have a pull request open to fix it. If that's a bottleneck for you, which honestly I have not seen many people seeing that as a bottleneck, you can use a Scala API. I think in a quarter or two, that limitation goes away. Hope you found this helpful. And if you end up implementing it, please write us a comment. Feel free to reach out. We are happy to help. Yogita, thanks for going through this. Thanks for building this end to end demo.
Yeah, absolutely. It was a great learning experience to be able to do structured streaming using real data. It was really valuable. I hope people find value in this and learn something from it.